We are following the law. Following the law means that we are following the law of conservation of matter, law of conservation of mass. Matter is neither created nor destroyed. So the way we show us following the law is by that balancing with the coefficients. Do you ever add subscripts or superscripts through the balancing act? No, you shall not. You always make sure that that's already done by just simply writing your equations correctly. You know, old school to us now, we know how to write nomenclature out appropriately, and then we're going to balance with coefficients. Indicators of chemical changes, Maddie's group. There's 5 of you. Okay, so color change could be an indicator of chemical change. Something else at y'all's table. What else could yield an evidence of chemical change? Say again? So the chemical composition changes? Okay, I like that. Chemical composition changes is like the absolute, if you knew the formula, see the formula changing, it's an obvious chemical change. But what if you can't see the, you see these powders and these liquids and these gases, like, it's hard to tell their composition, but I will say, from that standpoint, chemical composition changing could be a good one. One more at y'all's table. Well, see, evaporation condensation to me means state change, physical change of like I'm going from a liquid to gas or gas to liquid, but I myself am still my composition. I'm still water, but I was water as a liquid or water as a gas. So that's actually the same compound, right? So maybe give me, there's something you're saying that's right, it's just you've said it incorrectly. So, Nick, pick up.
Oh, bubble.
So gas evolution?
Yeah.
So I think that's what you were talking about. Gas evolution, meaning new gas is forming, not like, oh, I'm evaporating, like a totally new gas is forming. What's another one, Miles' group back there? Precipitate formation, right, that's a solid forming. What else could you maybe feel you couldn't really see? Emily? Heat, right, heat or cold, right, lack of heat. So that temperature change for us could signify that there was a chemical reaction happening. We don't see it, but we can definitely feel it. And that's a good holistic look there. Kim's group, what does diatomic molecule mean and when do you write them? I'll smile at you as you guys keep smiling at me. Whenever you're ready, maybe start with the first one. What does diatomic mean?
2.
Okay, 2 what? 2 atoms together. Okay, give me an example, Margaret.
H2.
H2, okay. When do I write this diatomic molecule? Do I just throw it in whenever I want it, or are there specific times? Like, for example, if I had an acid, right? Hydrochloric acid. Hydrochloric acid is, anybody? Hydrochloric is what? H, 1 plus, Cl, 1 minus, crisscross, you get HCl, correct. That's hydrochloric acid. But what I saw on some of y'all's, your test from last week, were that you were like, oh, it's got an H. That's a part of Big 7 and H, right? So some people are writing this diatomically within a compound. No. You only write H2 as a diatomic when it's by itself. And we're going to start to see that more often in a chemical reaction standpoint. It just cannot be combined with anything. Do not just put 2s on everything. It's only when it's by itself. Okay, when should you crisscross? Kyle's group. When should you crisscross charges and when should you not? Go ahead, Emily. Okay, this is my biggest issue. You guys are like the cream of the crop, smartest cookies on the planet. When I say charge, a charge, what does that signify to you? Matt, you think? What does that signify to you? Like, what does it look like if I say something has a charge? It's not your question. Let's do this. Robbie. It does not mean the number of valence electrons. It's related to that. Okay, so if I said the charge of something, you're talking about the relationship between valence electrons and octets, or what's, give me more.
It's either has like some more electrons than protons because they're
Okay.
both charged particles, but usually it's
So we're doing protons versus electrons. Okay, that is how we actually determine charge if we're looking at the subatomics by themselves. But then related to what you guys are saying, you added on X and what you added there.
How many of the user gains this out there?
Lose what or gain what?
Electrons.
Right. Okay, electrons lost or gained gives me a charge. And that's because it's different than the protons. That's because it originally, a neutral species has protons equals electrons, right? That's like sodium, potassium, chlorine, iron, magnesium, copper, anything with, if I just say the element, we're considering it neutral. But if we say an ion of that, an ion has a charge. And so guys, if you're writing ionic compounds and you're writing the charges up top and then you're crisscrossing them, you can't have one ion and not the other ion, because that's how they complete each other. Like a positively charged something has to attract to a negatively charged something. They have to complete each other. They have to crisscross in order to show that, like, hey, I have 2 pluses, and my friend here only has 1 plus. One negative. Well, that's not enough, right? I need to neutralize myself. So if I have 2 pluses, I need 2 of the negatively charged things. So I'm going to be MgCl2. Mg is a 2 plus, chlorine is a -1. I need 2 of them to complete me. So that's like this right here, if you're thinking in pictures. Mg2 plus has a chlorine and a chlorine. Well, we don't write that thing out like that, right? How do we write the formula? What's the formula of magnesium chloride? MgCl2, right? So we understand that there are 2 chlorines with a -1 charge, and there's 1 magnesium with a 2 plus charge, which is exactly this picture shows. But that we do that because a 2 plus, a 1 minus, and a 1 minus totals to a neutral charge of 0. We should never have hanging over charges. They always have been crisscrossed. So when do we crisscross charges? Well, the only things that have charges are ions. Covalents never have charges, ever. So please do not put a charge on something that's a nonmetal, because they will not donate electrons. It will only share electrons. It will not form a charge, because there's never a situation where the electrons are lost or gained. They are simply shared. Okay, so that's like really a big point we cannot keep having that misconception about. So charges means ions. Ions are in ionic compounds. Ions and ionic, yeah, sounds pretty similar. Never in covalent, yeah. Can you wait 1 second? We just got started here, yeah.
So you had an ion with 3 different elements. How would you crisscross those charges?
3 different elements probably means there's 1 ion and another ion still. So you need to look for your ions. So I'm glad you mentioned that, because there was an issue with how do we switch charges with, like, let me see what our quest here had. We had some people messing up on strontium sulfate. All right, strontium sulfate. Here we go. What's strontium? Okay, SR. Let me get my pen working here. SR. What group is strontium in? It's in group 2. It has 2 valence electrons. It loses those 2 valence electrons to form a 2 plus. Please go ahead and write this on the bottom of your quest. This is the last nomenclature-based question. And give yourself a chance to use this as review, right? Because we don't have TIL this week at all. So I'm using some of this time right now to do some review for you in the quest. Different colored pen is really preferred. That way you know what you did and then what you did not do, so that you can keep making improvements. It's all about growing here. We are, like I said, getting towards the peak of this, and I'm no longer baiting you on nomenclature. You should be getting the help you need or seeking it out from me or other people. Okay, sulfate. Sulfate is SO4 2 minus. Sulfate does have 2 elements involved. This is what Nick was asking. I have 3 elements here. I have strontium, sulfur, and oxygen. But sulfur and oxygen are not 2 independent. They are together. They are sulfate. Do not break up sulfate. The 4 is oxygens. Put a parentheses around your polyatomics, that way you never mess them up. So when you pop that here, SO4 stays together. Do not take the 4 away from oxygen. It is a part of sulfate's formula. But then this 2 minus and 2 plus up here, those are the charges. So how many strontiums do I need to negate this charge of sulfate? So I have sulfate with our strontium with the 2 plus, sulfate with the 2 negative. How many of each of these do I need to negate them to make their overall charge of 0? I only need 1 of each, right? Well, you can see that from your charge kind of logic. But also when you crisscross your charges, SR2, SO4, 2, some of you guys left it like this. Your ratio truly is correct, but that's not how we write empirical formulas. We always have to reduce them to their empirical formula. Empirical formulas are the lowest ratio that they can exist. Do not touch the 4. The 4 is not a ratio. The 4 is describing oxygen's number in sulfate. So the only thing you're going to do is reduce your 2's down to 1's, because this 2 divided by 2, this 2 divided by 2 would be down to 1, which is what you just said. You need 1 strontium and 1 sulfate to negate each other. Okay? So I just want to keep reviewing this because we're going to be using it a bit today. So while we're hitting nomenclature, let's go back up through that nomenclature 1 through 18. I want you guys to talk in groups for 2 minutes right now to get some of your questions answered. Correct them as you go. You know you're going to have to correct this regardless. Everybody in the room, say this with me now. I will correct this by Friday. Okay? That means you now know that this is going to be in the box by Friday, okay? So go ahead and take 2 minutes right now. Correct the nomenclature 1 through 18. Work with it, partner, at your table.
Joe, I was basically down for it.
I agree, but it tends to distract you somewhat. But if you're true,
Because you have to keep
parents have an
Oh, I got
That's what yeah, that's what yeah, I was
I didn't know what the prefixer said. Okay. Where'd you get 3
I know it's very today, but I'm
I got nothing. Wait, what? Oh, duh. You only messed that one up.
I put it
Oh, father. Oh, I forgot what the
like, and then I put the wrong
Oh, for what? Oh, I got the formula wrong. I got 1 through 7 correct. Oh, that was not too perfect.
Oh, just kidding. I got the formula wrong.
Whoa, there's... Oh, 17? Oh, that was what I got that one wrong.
I just give you a real life name.
Oh, wait, 17? You said 17?
Oh,
Oh, yeah.
17?
oh, dang it. I know the one.
What's oh my gosh, I didn't know.
Is that Lord?
I did that. I did it right. I didn't have that.
On the multi? Oh, that was C. I was so smart. Like, all this stuff to do is this D and D. I get a lot more than that. No, I actually literally, she's like, we have 15 minutes. Shoot.
You guys get 9 hydrogen.
Wait a minute. It was disapproved.
Alright guys, take 30 more seconds where you are, because we do have actual new stuff to talk about today as well.
My stuff was up with 0. Okay, I missed number 8 because I forgot what the charge was.
Number 3.
Alright, a couple of rules of thumb. So close your conversations in 5, 4, 3, 2, 1. Rules of thumb. And guys, I can keep saying this a million times, but you will never know it unless you say it to somebody else yourself. Literally, talk to your dog in chemistry. Teach your friends the difference between carbon dioxide and potassium chlorate, okay? Like, start talking it, because if not, you will never do it for yourself, and you're going to be stuck because we have like 2 more weeks of this, at least. So please do something for yourself, because I've already given 75, 100%, and I still got people giving me 10%. Okay, so non-metal, non-metal, that's when you use your prefixes, and those prefixes also describe the subscripts. Do not crisscross, please, and I will yell at you, because there are no charges. You do not crisscross charges. It's describing itself. Those only end in I. There's no funky endings to covalent compounds. Ionics end in ates, ites, or ides. No method. There is a method to the madness, except it's just not clear sometimes. That's when you are going to be using charges, because ionics, ions, they have charges. You have to find both their charges and crisscross. And then Roman numerals, of course, will always be with transition metals that have a variable charge. Do not just put Roman numerals on everything. You're like, oh, I think I'll tell you it's charged. Do not tell me magnesium's charged. Magnesium's charged at 2. We both know that. You don't got to say it, like as a Roman numeral. Aluminum is not a transition metal. Do not put a 3 Roman numeral on aluminum. It always has a 3 charge. Zinc is the same story, but zinc is a transition metal. It's just one of those ones that has a standard charge. Acids have the H in the front. Your variations of naming will be hydroic acid, like hydrochloric, hydrobromic, hydroiodic, hydrosulfuric, hydrophosphoric. Hydro does not mean acid. What does hydro mean? It's a binary acid, right? The acid on the end means acid, and that means there's an H in the front. But it's a binary acid, it's H with one other element. But if it's one of these that end in, ic acid or os acid, those don't have hydro in the front. That means it's not binary. So what do you call those other ones that have polyatomics in them? Ternary acids. They're bigger. They don't just have 2 elements. Okay, so we're going to be using nomenclature a bit today. And with that, we're going to walk through actually, we're going to only walk through 2 or 3 types of chemical reactions today. We're not going to go through all 5. It's a little bit overwhelming to do 5 at once. And so I'm going to show you guys cases that you will have to memorize, apply, and also analyze. There's multiple thinking skills today. If there are extras, then just put them on the desk right there. So please put away your quest for now so I can have your undivided attention. I'm going to put it to the side. So, say again? Oh, H in front, and then it says hydroic acid. Yeah. So we're going to talk about. Oh, let's go through the 5 again. What's one of the types of chemical reactions? Audrey, what's one of the types of chemical reactions? Okay, single replacement. We're going to do that one tomorrow. Kyle, another one. Double replacement. Okay, we're going to do that one tomorrow. Promise. Say again? We already said that. Combustion. We're going to do combustion today. Nick. Another type. Suffrage. Decomposition. We are doing decomposition today. Carson. We said single, double, combustion, decomp, and last one? Synthesis. Okay, so we're going to start with that synthesis today. And I expect that from me giving you 2 reactants, You know their names. You know how to predict which of these 5 they will take on, which of these 5 reactions they'll do. So the way you predict it is you know their patterns of reacting. So I'm going to give you a minute. We have the general, we have the 2 types. So you're going to write down all of this to help yourself. This needs to be very organized in your notes, because I will constantly say, refer back to your notes, refer back to your notes. I would not just recommend writing on the back of the piece of paper I gave you, because then you I'm giving you about 3 minutes, 4 minutes to write this down, because I have some examples I'm going to do with you as well. Having that lemon just kind of out near that stuff like see that is there. I'll come right back here and give you a check. So we talked briefly about how you can visualize the synthesis always taking 2 individuals and smooshing them together into one, which is this general form. The only thing that is really 100% of the time a synthesis is usually when it has one product. So our one product is here is listed as AB in our general form. The only thing you absolutely have to consider is that reflective nona. Is my product an ionic compound? If your product is an ionic compound, you have to make sure you're using your ions with their appropriate charges in your crisscrossing charges, CCC crisscross charges, if it's an ionic compound. So in this particular example with the binary synthesis, we are taking a metal and a nonmetal, and that they naturally always make ionic compounds. So if I'm taking them and I'm pushing them together into this, whatever this is, I have to make sure that I take their charges and I crisscross their charges to make their appropriate formula. And then after that, after we get all our formulas down, then we will balance. BCE is balanced chemical equation. BCE balanced chemical equation. So after we get our formulas there, then we will balance. Do not try to balance beforehand, because if not, you're going to have not the appropriate equation, and that would mess up a little bit more in terms of your stoichiometry you'll do later. So that's just simply a binary one. Then we have some that actually are a little bit more complex, because they're not 2 single elements. They're 2 compounds. So this is a compound, and this is a compound. And this is using our appropriate vocabulary way back from Unit 1. We said compounds are 2 or more elements. Well, we do have 2 or more elements. We have a metal oxide, and this could be any metal. This could be copper 2 oxide, sodium oxide, potassium oxide, beryllium, lithium, cesium. I could literally give you any metal, and this is just the general format. Metal oxides in water always make metal hydroxide. The OH right there is that polyatomic ion. Who's OH again? Polyatomic ion was hydroxide. So you could basically see the metal and then this oxygen and these H's mesh themselves into a single polyatomic ion, which is the hydroxide, so you get a metal hydroxide. So that's our first one. This is our second one. Those are the only 2 types, really, of syntheses that you're going to see. So I'm going to show you a picture here of a metal oxide. It's towards the bottom, so I'm going to scroll down a little bit. So this is a Actually, it's not a metal oxide. This is calcium. There's just 2 atoms of calcium. This is oxygen. You can see it's written as O2. Why is it written as O2? Because it's a diatomic molecule, and if it's by itself, you must write it in its diatomic form, which is O2. And then how did I just get CaO? Just CaO, no 2s, over here as a product. So ignore the balancing part. The balancing part came after we got our formulas. How did I get this formula is what I'm asking. So that is true, but that's because I've balanced it. Ignore the fact that it's balanced. How do I originally, the moment I see this equation, I see a calcium, I see an oxygen, I see a binary synthesis. What am I doing to make my formula at the end? Nick. What kind of compound is this, guys? It is ionic. How the heck do I get an ionic formula? Crisscross charges. Do you see charges here? No, because what happened? Calcium has a what charge? 2 plus. Oxygen has a 2 minus. In the end, crisscrossing, originally when I crisscross them, I get Ca2, O2, but then what do I notice I have to do? Reduce down to 1 and 1, CaO. Okay, please don't forget that. That's an ionic compound. You know how to do that. You know how to crisscross your charges. It's just in a different application at this point. Okay, so let's do some practice with this. So this right here, these are not on your paper. Write down the formulas, not the words. So I'll do the first 2 with you. Hydrogen. How do I write hydrogen? H2. H2. Good. It is a diatomic. You don't write it singly. You write it as a diatomic. Plus chlorine. How do I write chlorine? That's a good start. Is it a part of the diatomics? Yes, Cl2. Okay, don't forget your diatomics are big 7 hydrogen. The big 7, again, is made up of here. Go for it. Nitrogen, oxygen, chlorine, bromine, iodine, and hydrogen. I will write down the word every day, but if I have to. Okay, so what kind of reaction is this? Of my syntheses, which are the 2 types I have 2 to choose from, binary and the metal oxide one, which is this one. Binary. Okay, so I have to smush these together, but when I form their compound, this is going to form an acid, and I know that because I see this H that's going to be involved. This H probably is going to be an H plus. So truly, it's H1 plus because that's what hydrogen always forms. What does chlorine always form? A 1 minus. Say again, why? Because it's in group what? It's in group 7, and it forms a 1 minus charge because it gains one electron to look like a noble gas. So H plus Cl1 minus crisscross. What do you get? HCl. Okay, name that. What's HCl? Hydrochloric acid. Good. Okay, so that's going to be reviewing our naming. So then I see that it's not balanced. So what do I need to do to balance? Put a 2 in the front of HCl. We're done. Okay, so we formed our formula first. Then we stopped and we balanced. Okay, magnesium plus oxygen. Caleb, go for this one. Magnesium plus oxygen. Tell me my elements.
So magnesium.
Mm-hmm. So Mg. Yeah. Okay. Plus. How do I write oxygen?
O2.
Perfect. Okay, you guys at your table, 30 seconds. Write down the formula for what forms. Yes. I'm seeing that I have 2 elements that are being combined, and I'm making an ionic compound. This again is 2 elements, simply just simple elements, not true compounds that are coming together. And this one's going to make an ionic compound. And raise your hand on maybe over here, Chloe's table over here. What's the compound that's made? So magnesium oxide, MgO. How did you get MgO? Okay, so you took to the side of your paper. I have ions. My ions have charges. My charges are 2 and 2. Crisscross, and you get Mg2O2. But we can't write that. We have to reduce down to MgO. You guys with me? Shake your heads or something. Yeah? Okay. And then balance it how? got a 2 here and a 2 over here. Caroline, does that answer your question?
Sort of. What does it mean, like, in the first one? Why do we carry the chlorine inside compound?
Because it, whenever they exist as a, because this is a true reaction, right? Like I could do this in my fume hood back there. Chlorine gas is poisonous. That's why I have to do the fume hood. There is no such thing as Cl gas. I would never be able to find this. So this is appropriately showing how they exist in nature. Because there's no single Cl unless you're in aqueous form. And we're not in this case because it doesn't say so. All right, barium oxide plus water. So we just did 2 of the syntheses, yeah? No, there absolutely could. Absolutely. This one, just in this case, the 1 and 1 drop down and the 2 and 2 cancel each other out down to 1s. Absolutely, there will be some. Okay, we'll do some shortly. All right, barium oxide plus water. Barium oxide, shout it out. Formula. It is BaO, because that's, again, barium 2 plus, oxide 2 minus, crisscross, Ba2O2 drops down to BaO. Don't forget that this is happening. We're just dropping to the final. Okay, plus water. How do I write water? H2O. Okay, so this is the example of metal oxide plus water. What do metal oxides plus water form? You just wrote this down. Hold on. Metal oxides plus water. The general format is forms a metal hydroxide. Okay, so what's our metal in this case, Nick? Okay, barium. And barium has a what charge? It still has a little 2 charge. I'm just going to write that up here. It's not my final answer. It's just helping me get there. And then hydroxide has what? It does have a 1 minus. And please put parentheses around your OH so that you don't forget to put it at the end. So barium hydroxide makes BaOH 2. Okay. Is this balanced?
No.
State why.
There's 2 O's and 2 H's on both sides.
There are 2 O's, and there are 2 O's here, and there are 2 H's, and there are 2 H's here, and there's 1 barium and 1 barium. It is balanced. Yes, ma'am. Caroline.
So you're always gonna have, like, with the metal oxide, you're always gonna have OH and
I'm going to tell you 2 now so that you don't forget that, because if you did not have it on this one, for example, you would put BaOH 2, and that 2 would only apply to hydrogen if you did not have a parentheses there. So I'm going to say yes to protect you from yourself. Okay, last one, guys. You guys write this down on your table. Talk to each other. Zinc and iodine. I'm moving a little slow right now, so I'm picking up after this. It reformats itself at 3 dimensions atoms. The H on the O's get broken apart. Using the non-changing form, which is how the OH forms. All right, Lindsay's group up here. Tell me what you guys got. Lindsay and Jillian Chloe. So zinc. Give me. Okay. No, not 2 plus. It's just straight up zinc. It does not say zinc ion, right? It doesn't say zinc ion. It's just straight zinc. Plus I2, because that is a diatomic, yields Zni2. Where is this 2 coming from?
Zinc 2 plus charge.
Thank you. Please, please, please. When you see this, do not think that 2 just was like, oh, we just smushed those together, and I just came along for the ride. No subscripts come along for the ride unless you're polyatomic and you just don't get changed. This 2 is saying I have 2 iodines. This 2 is saying I have 2 iodines, but it's simply because of the zinc 2 and the iodine 1 minus crisscrossing to negate their charges equally. So that is Zni2, and it's balanced as it is. Yeah.
Why is there a 2 at the beginning?
This one? Where do you see a 2?
I don't get how that 2 for the iodine.
This is a diatomic, so we have to write it in its elemental, in its molecular form. And so it's not just I. Question? Because this right here, this formula is neutral, right? This formula is neutral because it contains 1 zinc zinc looks like this, right? Zinc has a 2 charge. It has 2 iodines, each with a 1 negative charge. And so this formula is neutral due to the fact that there's enough charge balance here to make it neutral. So there's 1 zinc and there's 2 iodines, so that's a 2 plus, a 1 minus, and a 1 minus, which total to 0, right? And so I require 1 zinc for every 2 iodines to make a neutral ionic compound. So these charges, you're right at crisscross, but it's because of this whole, I need 2 of these and 1 of these to neutralize each other. So they're, at that point, they're no longer charges, they're describing the quantities of them in the compound. Good question, actually, really good question. Okay, I'm going to pause on this one for now. Let's go ahead and switch modes to decomposition. So decomposition's our next one. I'm going to have you guys practice some of these alone later. Decomposition. This one has 4 types. This one's probably the hardest one. So I like to do this one first so that you don't have, so that you have time to like let it sink in basically. Because it does take probably 2 or 3 days to let this sink in. So I'm going to be quiet and let you guys do that first. Scroll down just a little bit. Does anybody notice something about the first one? Something eerily familiar. Okay, I heard 2 people say it's like synthesis, but what? It is definitely 100% just the reverse of the first synthesis reaction you just learned. Binary synthesis takes 2 into 1. Binary decomposition takes 1 into 2, giving them back their original form. So that's not hard if you remember that it came from the synthesis. Yeah.
Radiation, fission.
Yeah, exactly. Fission and fusion. Except fission, fusion, fuse nuclei, which are the nucleuses, whereas this is a compound. Same story, different concepts, but same thing. All right, I'm going to scroll down a little bit for you. You should be able to find another one that's simply the opposite. I'll come right back down here. I'm going to go ahead and ask now, what is the other one that looks very similar to synthesis but opposite? 1, 2, 3, or 4? 3. Okay, metal hydroxides, like we just formed, we're going to break them back down into their original elements, which were our original compounds, metal oxides, and water. So there's not really 4 new ones, there's only 2 new ones. Got it? So if you see that semblances, then you're good. So one thing that you need to make sure you do know is that there's a good amount of stability to a compound, right? So generally it's not just going to poof and make these new compounds. It's not going to just poof and decompose. Some things do decompose a lot over time, but it generally is going to take some sort of reactant or some sort of oxidant or heat or a lot of moisture. There's other conditions that are forcing it to decompose. So the one that we generally focus in on is that requires energy. And so the way you describe energy above an arrow is what again? Triangle, right. You say heat above the arrow like that. Question?
Would 2 and 4 be flipped to become a form of synthesis?
Nope, because these are gases, and gases generally it's harder to capture them and smush them into the reaction vessel. But you could, it's just I'm not asking you to memorize those. Don't put any more on yourself than you have to. Okay? I'm asking you to memorize these decomposition products and the synthesis products or methods, right? So that's why I'm really trying to make sure you see the semblances between them. Okay, so ionic compound breaks back down into metal and nonmetal. If it's a nonmetal diatomic, make sure that you do write it the diatomic as it should be written. And then the metal hydroxide, don't forget that this is a ionic compound. And so if it's ionic, you must crisscross charges. And that's for the decomposition of those. So the 2 that are new here are the carbonates and the chlorates. So I want you to remember, most of the time decomposition products are gases. There's a lot of times where they're gas. So like, for example, this diatomic here is probably a gas. This water could vaporize to form a gas. So I want you to think first in terms of what gases would form, and then the other ones fall into place. So carbonates sound kind of similar to carbon dioxide, or especially if you're looking at the formula, you see that there's some carbon and oxygen in there together. So carbonates will always decompose to form carbon dioxide. Okay? Well then, if it's carbon dioxide is one product, you have to kind of fill in the gaps with the rest of the product. It makes sense that one of the oxygens gets stuck with the metal, because there were 3 over here and there's 2 over here, yes? So metal oxides, again, metal and a non-metal is ionic, so you must crisscross charges to make sure you have the appropriate formula, but that's it. If you know the gaps, you know the other compound, very, very easily. So carbonates form carbon dioxide. Okay, so then in your mind, you're like, yeah, chlorates kind of sound like they should form chlorine, right? But chlorine would kill everybody in the room. And we're doing these reactions. We're actually doing these. I'm not going to make a hazardous gas that's going to kill us all. Okay, so let's just go ahead and make that straight. It does not form chlorine. So it forms a more friendly gas, like oxygen. Okay, more friendly gas. So chlorates have some chlorine and oxygen in it. Pull out the oxygen, make some oxygen. But then you're going to go, well, there's 3 oxygens there, and there's 2 here. That's because simply I have a general format, and I don't have it balanced, because I can't balance it without knowing the metal at this point. But then the metal and the chlorine they're going to stick together to form the metal chloride. Again, this is ionic, so you must crisscross charges to make sure you get the appropriate formula. Okay, so let's do some samples with these, and then I'll have a demonstration for you guys as well. Okay. So, sodium carbonate. Actually, you guys go ahead and write down the formula for each of these. We're going to do each of these separately, though. Write these down as your decomposition reactants. Many of you mistakenly put sodium carbonate on your test as NaCO3. It's not NaCO3. What is it, Emily? Na what? 2CO3. Good. That decomposes. Okay. Don't look back at your notes. Metal carbonates break down to form what gas? Say it loud and proud. Carbon dioxide, right? Carbonates make carbon dioxide. 1 second. So if I'm a carbonate, I have to break down to form carbon dioxide. I don't care if you put carbon dioxide first or second, it doesn't matter. I'm going to stick with my format so that you can start to ingrain this in your brain. Okay, so carbon dioxide is made. What is the other thing that sodium can bond with to form the other product? Okay, so a metal oxide is formed, so sodium oxide is formed, so then your brain, you're going, sodium has a charge of 1 plus, oxygen has a charge of 2 minus, crisscross, and you get Na2O, sodium oxide. Okay, so that nomenclature is coming back, right? Okay, so as we go now, we can balance. What's not balanced here? Give me a thumbs up if it's good. Okay, it is, right. There's 2 sodiums, there's 1 carbon, there's 3 oxygens total. 1, 1, 1 would be our ratio. Okay, so carbonates break down to form carbon dioxide. What do chlorides break down to form? Oxygen. Okay, I'm just trying to make you say it out loud because you will say chlorine on your test. Potassium chloride is K, not P. Don't be that person that puts potassium as P. Okay, potassium, what's chloride? ClO3. Okay, that's a K1 plus. ClO3 is a 1 minus. Right, crisscross, you get the same thing. Okay, that breaks down to, you just told me what gas does chlorate form? Oxygen, something friendly, right? And what has to stay together then? The metal chloride. So I don't want you to forget that it's not just going to be, it's not just going to be the whatever's stuck here. Because like, for example, magnesium chloride, not just MgCl, right? It's MgCl2. Don't forget you are still crisscrossing. K1 plus, Cl1 minus, crisscross, you get KCl. Is this balanced? No. So what do I need to do first? What do you see is not balanced? Okay, so I see 3 in oxygen, I see 2. So I can't just multiply by 1 to get the other, so I have to do the least common multiple thing, so multiply them both, correct? So what do I put over here? A 3, so that's 3 times 2 is 6. What do I do over there? But where do I put the 2? I have to put at the beginning. Please don't squeeze a 2 in the middle of this compound. Then you have changed the formula. That is a 2. Okay, so now that 2 applies not only to oxygen, but also potassium and chlorine. So what do I need here? A 2 as well. Okay, give me a thumbs up if that one makes sense. Awesome. Okay, water. I know we know that formula is H2O. What kind of decomposition is this? 1, 2, 3, or 4? Look back at your notes. Binary, carbonate, metal hydroxide, or chlorate? Say again? I heard it back there. Caroline? It's binary. Do you see a metal here? It's not metal hydroxide either because there's no metal. Yes, water has hydroxide embedded within it, but that doesn't matter. It is binary. Binary means we need to break it down into its 2 elements. Well, what are the 2 elements that make up water? Hydrogen and oxygen. Okay, done, right? Who said no? Thank you. All of you should say no. This is ugly. Ooh, what has to happen with my elements here? Okay, so I heard O needs what? Okay, this is a diatomic molecule. What about hydrogen? It is diatomic as well. Make sure that you recognize when they're diatomics because that's going to affect your balancing. Those have to be diatomic because they are singletons and they're in the big 7 hydrogen. Now I can balance because I actually have my formulas right. What do I need to balance? Hydrogen is balanced, right? I need something. So oxygen, there's a 2 over here. So then what do I need over here? 2 over here. So that, 1 second, Caroline. So this oxygen having a 2 means I need a 2 applying to this 1 that's out here. But that also applies there. So the hydrogen with a 2 and a 2 means I have 4 hydrogens. So then I need a 2 over here. Did I answer your question?
I thought we weren't supposed to use the 2.
Which 2?
The one that we got from the diatomic.
You're using it to balance because in terms of like if you're looking at this, you can definitely see there are 2 oxygens here. That's no question. There are 2 oxygens there, and there's only 1 here. Then that's not abiding by the law of conservation of matter. So we do have to balance that way. So I don't want to reinforce any negative misconceptions there. Okay, pause here. let me show you what potassium chlorate decomposing looks like, okay? So come back to my office, which is the humidor. Let me give you a second here. Grab some goggles. Stand back and be ready to be wowed. Okay. Wowed. Just kind of stand like a big semicircle right here. Semicircle. You don't have to have glasses on unless you're right next to me. And just kind of come up here for a semicircle. All right, so I have my magic Bunsen burner. And make sure it's set up. How do I set up Bunsen burner? Righty side me, and then what? Give me some help here. I have one half turn on the bottom, and then I need righty sidey on the barrel, and then 8 half turns on the barrel. 1, 2, 3, 4, 5, 6. So, now what I have in my test here is potassium chlorate. What is potassium chlorate decomposed to? Oh no! Alright, so I've got my fire. Okay, so what I'm going to do is I'm going to apply heat to this decomposition reaction. My potassium chlorate breaks down to what? Okay, so oxygen gas is getting made, and KCl. So I'm making this molten right basically. Let me take just a minute because just saying. So while this is heating up and melting, where do you guys know oxygen is used in your body? Cellular respiration. Okay, so what is cellular respiration? Making energy. Okay, so now my phone is on. Abby, can you turn on the Okay, so I'm slowly melting, slowly melting. Let's get the, thank you. Okay, so it's melting, melting. So cellular respiration reacts with what in your body to make energy? Glucose. Okay, so where would you find glucose in everyday, kind of life? Okay, more specifically. Okay, what kind of food has sugar? Lots and lots of sugar. Carbohydrate. Carbohydrate is an example of glucose, but what food would you find glucose in a lot? Sugary foods, like maybe if you're going trick-or-treating. Oh, candy, okay. That's fine, you're gonna let them know. Okay, so I now have decomposed. Okay, whoop. You see I decomposed it. Does that look like anything really happened? Okay, it kind of melted, right? It turned molten, but if you were closer than you are now, you would see oxygen bubbles coming out the top. But you wouldn't really know it's oxygen bubbles until I proved to you it was oxygen bubbles by showing you that a decomposition. Oh, so I'm showing you there's oxygen gas because it just is destroying that glucose in that gummy bear. Like, destroyed it. That's a gummy bear? That was a gummy bear. You guys want a gummy bear? Here. Oh, it's hard as a rock. You don't want that one. Okay. So, I keep really still gummy bears for this reason. That's just me. Okay. So, I proved to you that oxygen gas was being made because what did it then force to happen? What did it do to that gummy bear? Don't say it destroyed it. Give me something technical. It combusted it, right? So that basically, we talked about last week, that combustion was when oxygen is present, it makes a reaction occur. Sometimes syntheses, synthesis and combustion can be very similar. But combustion is like you can tell combustion's happening. Like you can see it happening. And also, you can't tell, but there's carbon dioxide and water vapor coming out of that. And it's also going to be this great smell of s'mores here shortly, so I'm just going to kind of let that happen in the room. Because your tummy's going to be grumbling. But you can definitely tell it burned. You saw the fire. You saw it burn down here as well. Okay, so that's the death of the gummy bear. No! Whatever you got to do to recognize that it just died for your education. But now back to your seats. I didn't tell you that's my back. Thanks, Robbie. What alarms? I don't know what alarm was going off. Okay, so we just did the potassium chlorate example in a few minutes. You guys go ahead and write down the decompositions of these. And I'm telling you it's decomposition, but if you were like looking at this, would you know that this is a decomposition reaction? If you just saw this up there and I said, what kind of reaction is this? I mean, could it be synthesis? Could it be synthesis? No, there's no other thing, right, to combine it. There's only one. There's one compound. That one compound can't do anything but break down, and that's going to be decomp. So go ahead and write down your formulas and then predict the product. Yes, if it's a compound, yeah, because that's a compound, right? This is an ionic compound. And you know how ionic compounds work? They have their charges and you crisscross them.
So if it's covalent,
If it's covalent, you don't. Correct.
so which one would you use for? You don't have set up for ones like that.
Yes, we do.
You do.
Yes, it's one of the four. I will tell you, you guys need to get a water bottle like this. You don't have to carry it around here on the table. It's very handy. You're doing your homework. But just tape up here on the table to your water bottle. People just look at you weird, but it's good. Alright, formula for magnesium chloride chem. So loud and proud. Calm down. Kim, calm down. Emily, what does it break down to? Whoa, 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 hold on. There's no O, right? Because there's no oxygen here. So you said magnesium, right? So first off, Jacob and Kimberly is with me. We recognize this as which of the four decomps. It is a binary one, right? It's just a metal and a non-metal. We're going to break them apart. So metal and non-metal break into metal and non-metal. Metal being magnesium, and the non-metal being who? It is chlorine, but then again, you're going chlorine can't exist as Cl by itself. It has to be a diatomic, and that diatomic is simply because we know the rules of diatomics, not because that two there came from magnesium's crisscrossing charge. It just so happens to balance itself as well, though. Okay, so think about why you're doing your charges, why you're writing it diatomically. They're going to be different things. And it's balanced. Calcium hydroxide. Jacob. Beautiful. So each calcium is a charge of 2, hydroxide is a charge of 1. Crisscross them. Good. What do metal hydroxides break down to? This group over here. Metal hydroxides break down to metal oxides and water. So I know water's formula. I'm just going to write water by itself now. What is the metal oxide in this case? Calcium oxide. So calcium oxide is just, happens to be CaO, but not because it's calcium oxide, because it's a 2 plus and a 2 minus, crisscrosses down to 2 and 2, reduced down to 1 and 1. Okay, and then is this balanced? So it happens to be balanced. Okay, so at this point, I'm going to pause for about 5 minutes. You have a series of 10 questions that are on this sheet that I copied for you. 1 through 10, so it's 5 from synthesis, 5 from decomp. I'm giving you 5 minutes to get started on that now, so you can ask me questions on synthesis and decomp before we move on to combustion. I'm still walking around here, so you have 5 minutes to practice, so you can ask your questions now. And by the way, when you are writing this on paper, if you're writing on paper, do not push next to the words with an arrow. You need to write out fully the reactants yield the products. Do not just put an arrow next to the letters there, because that means you're not writing the reactants out. Arrow? What do you mean? So, 1 second. Let me write that on the board. So these you must write out reactants build products. Do not just put an arrow next to these letters up here. Just do what we've been doing in class. Just do what we've been doing in class. Yeah, what we've been doing. I'll jump to some decompositions too, so you can make sure you ask good questions.
You do not like this. Absolutely, it's not wrong. It's just an element. It's not something that produces students that produces just like you to reactions. And we don't think about it. This is
choose to do that.
because it's true. It's a compound, and that compound is ironically supposed to start as yes.
Lindsay, somebody from y'all's table? Somebody from the universe on the board? Now, whenever you're ready. And then Maddie, somebody from your table, will come and do your table. 3 on the board. Okay? Whenever you're ready, like 30 seconds. Somebody from that table?
Silver. I think we're
Alright guys, check your work up here. I want to show you another way to write water as well. So first off, number 2, thank you guys. This is zinc, and this is what I'm trying to like very make clear. Before reaction begins, they are simply elements, or they are simply compounds. They are not ions. Please do not put ion charges before the reaction begins, which is when it's in their reactant form. Reactants are simply compounds or elements, not ions. So make sure you're using your vocabulary to really enforce, like, do I know what ion means and do I know what an element is? Okay, at this point, this is all background knowledge for us. Zinc is plain old zinc. It's a piece of metal chilling on the table. Sulfur is just sulfur. It's chilling next to it. They're two separate things. But once in this yield symbol, this is when they start to kind of get together and they start to kind of change up some of their electrons and they get to make ions. And during that time, you don't see that. You don't see it. It's just happening during a reaction. It might look kind of cool, but you don't see the ions exchanging. But you know they do, because that's what metals and nonmetals do. They form ions. And so before I made it to that product form, zinc had made a 2+ charge because it had given up 2 of its electrons to sulfur. Well, how did I know these charges? First off, zinc is a memorized one because, right, it's a transition metal, it has a standard charge. How do I know sulfur's charge? It's in group 6 and it always forms a -2 charge. So zinc gave up 2 electrons. 2 electrons given up to sulfur, and that's how it got its 2 negative charge. Well, when we form this, we show the ionic form at the end after it's dropped its charges from 2 to 2 to 1 and 1. And that's what this is right here. But during that exchange, you know it's happening, but you don't write down the ion charges anywhere until you make the final product. Okay, and then metal oxide, sodium oxide, and water. If you would like to write water as H2O, that's fine, or HOH, it's the same formula, it's just split. But this might inform you that it's forming a metal hydroxide. So I'll show you like kind of sodium and the hydroxide make sodium hydroxide, but then this O and H here will also need to be accounted for in the balancing. But it doesn't matter, you've memorized that metal oxides and water form a metal hydroxide. So the metal hydroxide is sodium hydroxide. This is sodium with a 1+ charge. This is hydroxide with a 1- charge, 1 and 1 crisscross down. Where did I get this 2 from over here? So 1+ from sodium, 2- from oxygen, crisscross. This is ionic, this is not ionic, this is ionic. This has to be balanced though, so I put it at what, where? To where? In front of the sodium hydroxide final product. So that's 2 sodiums, 2 oxygens, 2 hydrogens, 2 oxygens, 2 hydrogens. So I am balanced, yes. You have to use charges to form the compound's formula. But like, for example, if I am just an element and I have a 2, if I'm an element and I have a 2+ charge, that means you're talking about my ion form, not my element form. My ion form has a 2+ charge, but that's because when I'm forming an ion over here, those charges are crisscrossing. But you see, I utilize charges to make my formula, right? That's how you've been doing nomenclature all your chemistry life now. Don't forget that. So when I said that, I was talking about, like, if I'm forming my compound, I have to use my charges to form the compound formula. But like, if I'm just a single element, don't put a 2 here, don't put a 2 here. That's not correct. It's just simply zinc. Okay. Yes.
So for the first one, we should put
Just a Ca. Please don't put a 2 by the O. We know that it forms a 2+ charge when it makes its ion compound finally. But here it's simply calcium. Here it's simply oxygen. Simple, simple. It starts to react, it starts to exchange electrons, it's exchanging electrons, and as it does that, calcium has lost 2 electrons. Oxygen has gained 2 electrons. Elementally, crisscross those, Ca2O2 reduces down to CaO. And then 2 and 2. You guys need to practice these. Okay, let me pause here for a moment. I have 15 minutes left. We need to go ahead and do combustion. I will review the rest of these with you guys tomorrow, but please, you will finish 5 on the first ones and 5 on the second ones. And combustion, I've just got to scooch down here some, because I'm doing combustion now. So, go ahead and write down your standard set of examples for combustion. Take 2 minutes here, please. So combustion is very apparent. It's easy to see. It's easy to see because one of the reactants has to be oxygen. When I say oxygen, I mean oxygen molecule, which in this case is O2. So O2 being a reactant sometimes makes it resemble synthesis, and this is what I was saying back there. It is a combustion of metal, meaning a metal plus oxygen yields a metal oxide, because this is basically binary synthesis. So this is going to be binary synthesis or combustion. They just basically act the same way when it's just a single element and another element, which in this case is oxygen. So in this case, this is an ionic compound, so you are crisscrossing charges. Don't forget ionics, you always crisscross charges to form the formula of the compound. Combustion of hydrocarbons. Hydrocarbons sounds like carbons and hydrogens, right? Hydrocarbons. Hydro kind of sounds like there's hydrogen. Carbon sounds like there's carbons. We generally we usually assemble it as C and H. This is like your benzene example from the CSI lab with the guy who died. Yeah, C6H6. It's just a hydrocarbon. And so in this case, hydrocarbons can vary in formula. And so I've just denoted as X and Y to show that those are subscripts that can vary. And it reacts with oxygen, and it always makes carbon dioxide and water. This is cellular respiration. This is this could be glucose plus oxygen yields carbon dioxide, water, and 36 ATP. If that were forming molecular or cellular energy, we can't really see ATP, but we saw that energy produced earlier, right? We saw it as a fiery pink flame, which energy is generally produced in a combustion reaction. So that's another fact. Generally, energy is produced. And so energy can come in the form of fire and flames, or just heat, sparks, light. Energy comes in many forms. And so that's sometimes what things you see with this. Now, this first one being binary means you can easily determine that formula. The second one's a little harder to do. That's because you're going to be expected to understand how can we write these hydrocarbons in different ways. Do you guys have your piece of paper that has organic chart and examples right here? I'm going to show you how you name organic compounds. So I opted, because we were on the struggle bus with nomenclature, I opted not to do this with nomenclature the last 2 weeks. So I'm doing this now with you, and I'm doing it quickly with you. You have a chart in front of you that should guide you. So the first part is, this is in your book, page 639 if you'd like to look there. But organic means not green and healthy and, no pesticides. It means has what? Contains carbon, right? So hydrocarbons obviously are going to be applying to that rule because they are organic in nature. And so this background information that you have on your paper gives you some information about carbon. It has 4 valence electrons. So if I have 4 valence electrons and I'm forming bonds, how many bonds would I want to form? Oh, thank you. So if I'm carbon and I have 4 valence electrons, how many more electrons do I need to form octet? I need 4, right? So if I'm carbon and I have 4 valence electrons, I need 4 more. I'm going to form 4 bonds like this. So C, H, 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 that means carbon has octet, right? So this is kind of some background information. You know that carbon needs to form 4 bonds to have octet, because that's how the valence electron system works. It also gives you some background information on things called functional groups, but we're really only going to talk about one. It's called an alcohol. Well, we kind of know alcohol is a compound. It actually has a OH on the end. I'll show you that in a second. But these prefixes, I didn't want you confused with your other prefixes. They are very similar, but not all of them are similar. So here's how you read this chart. You're going to use this chart until you're comfortable with this. If I am an organic compound, and I have 1 carbon in my structure, 1 carbon in my formula, this first name you give me is meth. If I have 2 carbons, eth. If I have 3 carbons, prop. If I have 4 carbons, don't say but, it's bute. Bute, okay? And then pent, hex, hept, oct, don, dec. You can keep going further. But these probably are very familiar to you, yes? But these top ones are not. M-E-P-B, you have to remember meth, eth, prop, and bute. So if I have a specific subset of hydrogens to go along with me, my name can change. I can be methane, I could be ethane, propane, butane. Which of those have you heard of before? Methane, califarts, okay? What else? Propane's gas put in your grill. Butane? Butane lighters, big lighters, or just add butane in them. Ethane, maybe you've never heard of. But pentane, hexane, heptane, octane, those all mean you have a certain number of carbons, and those carbons are fully saturated with hydrogens. They have enough hydrogens to make them have 4 bonds each. So let's draw an example of those. So go ahead and let's draw out ethane, 2 carbons, draw this on your paper. Ethane has 2 carbons, and it has every hydrogen is located on a carbon, making enough hydrogens so that carbon has 4 bonds each. So this carbon has 1, 2, 3 hydrogens, and this 4th bond is just with a corresponding carbon. And this one mirrors it with 1, 2, 3 hydrogens and a corresponding bond with a carbon. Are carbons happy with octet? Yes. Okay. What's my formula? C2H what? H6. Okay. If you see this drawn out like this, or if you see this compound name formula like this, you should tell me it's ethane. And the way you know it is because it follows the rule of anes. Anes are always 2n plus 2, where this n is the number of carbons. How many carbons do I have here? 2. So formula, insert your number of carbons. 2, what's my n number? Number of carbons? 2 here, okay? Plus 2 equals 6. 6 hydrogens. So in AIM, to give you the number of hydrogens, you do 2N plus 2. Do you see that on your paper, though? The top of your chart, where it says alkane and AIM. You see alkane, 2N plus 2? That's how you determine the number of hydrogens. So where it says functional groups, put number of hydrogens there, so you remember that that's how you figure out the number of hydrogens. But when I say alkane, I'm not going to go, guys, remember hydrogens are 2N plus 2. You need to remember that that's how you determine their formula. But if you draw it out, you should be fine. If you write it out like this, sometimes you're going to have to go from formula name or name to formula. All right, before I take questions, let me finish up this a little bit more. Okay, so let me go ahead and ask you then, what's the formula of butane? Using your logic and using your rules. Butane, what does but mean? Or what? 4 carbons, okay. And if I'm in AIM, what's my rule of thumb for finding my hydrogens? What's my rule of thumb? 2N plus 2. Lost my marker. AIM is 2N plus 2, so how many hydrogens should I have? 2 times, what's my N number? 4, because that's my number of carbons, plus 2 is 10. Okay, C4H10 is my formula for butane. What's my formula for pentane? Pentane. We're getting good at this. C5, pent means 5. H, so 2N plus 2 is 2 times 5 plus 2 is 12. Okay, so with this information, you should be able to do a combustion of butane, or combustion of pentane, or combustion of methane. So let's do one of those. I can finish going over a bit more combustion tomorrow, but you do have your rules in front of you. I think I've explained enough on how to read the chart. But let's do combustion of propane. Let's change this to propane. All right, combustion of propane. Propane combust. What's one of my reactants? I'm finishing this example before we go. What's one of my reactants? Pro. C3, H, 8. So everybody give me a thumbs up if you're realizing how we're getting the formula. So you're reading your chart. Pro means C3. AIM means 2N plus 2. 2N is 2 times 3 plus 2, because that 3 is coming from the number of carbons. So propane combust. What's it combust with, guys? Oxygen. What and hydrocarbon combustion always makes what? Two products. CO2 and H2O. Okay, so this prediction process for combustion is so easy because it always makes the same thing, right? There's no funky business here. But now I have to balance. How many carbons do you have here? 3. How many do I need here? So what do I add? 3 coefficient. Okay, let's ignore that how it distributes for a moment. I always balance the carbon first, and then I will balance the hydrogens, and then lastly the oxygens, because the oxygens are in 2 places. It's harder to balance that way. How many hydrogens do I have? 8. What coefficient do I need here? Say again? 4. Loud and proud for me, guys. I want to make sure we're good here. So that 8 and then 4 times 2 gives me 8 hydrogens. How many total oxygens are over here now? 3 times 2 is 6 plus 4 times 1. So there are 10 oxygens over here, because that's cumulative oxygens. So that coefficient does distribute to the oxygens. There's 10 oxygens here, so what coefficient do I need here? 5. So balance your C's, then your H's, then your O's. I want you to attempt the combustion section of 1 through 5 as well. So the 1 through 5 section that comes through here, you have synthesis, decomp, and combustion. So you have 15 reaction predictions tonight. So 15 reaction predictions. And then what I'll do is, after we get done tomorrow, I'm going to see our progress on the cars, polymers and cars. And with that, polymers and cars, you have your research on a 1-page paper. one cumulatively together with you and your partner. One page. Work on a Google document and share with me if you want me to look it over. I'll let you know when we're going to share them. We will not have time to share tomorrow.
Totally incorrect, so.
Oh, look. Thank you. Bye, guys.
Thanks, Emma. Thank you.
Bye. We did a lot today. Look it over so that you can ask me good questions tomorrow. I like your crimped hair. Or your, not crimped hair, your braided. We used to crimp our hair